Okay, this is the last topic of hashing. Okay, previously we talked about static hashings. So in the static hashings, we had overflow problems and we talked about how to design the hash functions, right? So actually we talked about the basic issues of hashing and we talked about the benefit of hashing. But the static hashing has some kind of problems. So to overcome that kind of issues, then we're going to talk about dynamic hashing. Okay, and in the dynamic hashings, there are two approaches. First one is directory-based hashing, or extendable hashing, or directoryless hashing. Okay, so we're going to talk about these two approaches. First, let's talk about dynamic hashing. Okay, so before talking about dynamic hashings, then we'll talk about the problem of static hashing. So in the static hashings, we waste some memory space sometimes. Think about the hash table. So before hashing, actually we have to allocate memory space. Okay, so we have to have a hash table, and then we will use a hash function to distribute all the identifiers to hash table. Okay, so in the beginning of this hash table, so when we have a few identifiers, then we are wasting lots of memory space. So we don't use lots of buckets in the hash table, right? So that's the waste of memory space. Okay, and also when an insert causes the loading density to exceed the pre-specified threshold, then we use array doubling to increase the hash table, the size of the hash table, from b to 2 times b plus 1. What does that mean? Okay, so when we have a hash table like this, okay, so in this example we have 2 slots for each bucket, then the loading density is higher than the threshold. So we have lots of slots with identifiers. Okay, so even when we have some empty slots, but still this is too dense. So probably when we insert another one, probably we're going to have a conflict and overflow. Okay, so if we have overflow, in this case, if we have overflow, then even with a really nice overflow handling, but still we're going to have overflow problems. So anyway, we have to increase the size of the hash table. That's the only solutions, right? So when we increase the table of the size of table, then we can double. Okay, so actually it's slightly larger than just the double. Is if it is a b and then this one is b plus 1. Okay, we don't like even number, so that's why we add b plus 1. So here's the problem. We increased the size of hash table. Okay, then what about these identifiers? They are already distributed to the hash table. So now we increase the hash table, then we have to rehash all these identifiers. Okay, that's the problem. Why is that? Can we use the previous hash functions for these identifiers, and then can we have a new hash functions for these buckets? That's not possible. In theory, that's not possible. If we have a static hashing, that's not possible. Think about it by yourself, okay? You will see why that's not possible. Okay, then we have to rehash all these identifiers. So actually, it will be something like this. Okay, so evenly distributed identifiers. That's what we want. Okay, so that's okay, but think about it. If we have like 1 million of identifiers here, and then we have more identifiers, so that we have to increase the size of the table. Then after increasing the size of table, then we have to rehash the previously distributed identifiers. So we have to rehash 1 million identifiers. So it could take unacceptably long periods. That's the problem. So basically, with static hashing, sometimes we waste memory space, and also sometimes we waste lots of time. Okay, so it means that's not that efficient. Is that the best thing that we can get? No, we can get a better one. If the number of identifiers is limited, like a couple of hundreds or thousands, then that's totally fine. But if you have a lot of identifiers, then the memory issue is a big deal. Then we can come up with a dynamic hashing. So it is actually extendable hashing. Okay, whenever we need, then we can make one more bucket every time. Okay, something like array and linked list. Okay, it's different, but they're analogically. So we are going to talk about this dynamic hashing. Okay, before going into any detail of dynamic hashing, let me explain what try is. Okay, so you can read this one like tree, but try is more convenient to distinguish this one from tree. Okay, so I will read it as try. Okay, try is a kind of search tree, also known as digital tree, and sometimes it's radix tree or prefix tree. Okay, so this one is somehow similar to BSD, binary search tree, but not. It's different from binary search tree. So look at this table. So from the root node, okay, so we follow the character. So actually we insert all the words into this tree. Okay, then to find a target word, then we are gonna follow the edges with the characters. So if we are interested in 10, okay, then from here the first character is T, so we follow this edge, and then the next one is E, then we follow this one, and then next one is N, and that's it. Then this is our target word. Okay, so it looks similar to BST, right? But it's different. In this try tree, we follow this tree with the characters. Okay, but in the BST, we don't follow the characters. We have keys, and based on this key, from the root node, we just compare our target key with the root node's key, and then depending on the result, if our key is smaller than the root keys, then we have to go to the left subtree, and if our key is larger than the root node keys, then we have to go to the right subtree. So depending on this comparison, then we move. But in this try tree, we don't compare. We just follow these characters. Okay, that's try. Okay, good. So dynamic hashing is closely related to a try. Okay, so let's use a binary representations. In the previous slide, we used characters, alphabets. Okay, so that in this node, we can have 26 children. Or if we have an upper character and lower character, then we have 52 children, right? But if we have a binary representations, it is binary tree. Each node can have only 2 children. Okay, so now we have a binary representation. So try is a binary tree in which we locate an identifier by following its bit sequence. So in the previous slide, we followed the characters, but if it is binary representation, we follow its bit sequence. Okay. And in the previous slide, we followed the first character first, and then second character and third character. But in the binary representations, in these examples, we are gonna follow the last digit first, and then the next one and the next one. So the direction is opposite. Okay. So we have an example here. We have 8 identifiers consist of 2 characters. Okay. So we have identifiers with 2 characters. It means binary representations. And then we build a tree with 2 low order bits as a key. Right, so if we have 8 identifiers, then 2 low order bits would be enough. Look at this one. So these examples, we have 2 lower bits to indicate this node. And in this node, we have 2 identifiers. In the previous slide, each node has just 1 word, but in this tree, we have a bucket. Instead of 1 word, we have a bucket with 2 slots. Okay. If you want, you can have more slots, but in this case, we assume that we have only 2 slots in each bucket. Okay. So with the 2 bits, then we can have 4 buckets. Okay, then we can have 8 identifiers here. So this is okay. So we follow, let me explain this try tree. Okay, so first we focus on the last bit. Okay, last bit means these ones. Then this is a 0, so we're interested in a 0. Then first one is a 0, so we follow this one. And then the next one is a 0, so we follow this one. So we have a 0 here. And second, let's try a couple of more things. So a1, first thing is 1, so we follow this edge. And then next one is a 0, and we follow this one. So we have a1 here. And let's try b1 too. The first one is 1, and second one is 0. We have b1 here too. Good. Okay. So now we insert c5 here. So c5 is here, and the first digit is 1. Okay. And second one is a 0. So it goes to this bucket. Oh, now we have an overflow problem. Then what should we do? Since this one is a try tree, then we can easily handle these overflow problems like this. So originally we had just 1 bucket here. Okay, we had 1 bucket with a1, b1, right? Now when we have an overflow, then we take 1 step further, breaking this bucket into 2 buckets. Okay, so now we add 1 more bit here. So a1 is here. So first one is 1 and second one is a 0. And then now we split this node into this bucket into 2 buckets by adding another digit, 0. So by adding 0, a1 and b1 will be in this bucket. Okay, and then by adding 1, c5 will be in this bucket. Okay, good. What if we had a1 and b5 here? Okay, let's assume that b5 has something 101. Okay, then we're gonna have a1 here, and then b5 and c5 will be in the new bucket. Okay, but anyway, we can split this bucket into 2 buckets, and then we can have all the identifiers. Good, there's no problem here. Okay, now let's insert c1 again. And the c1 is here. Okay, and then 1 0 0. So 1 0 and 0. So c1 is going into this bucket. We have an overflow problem again. Then what should we do? We do the same thing recursively. Okay, so we split this bucket into 2 buckets by adding another bit here. So now c1 and a1 has the same kind of pattern, and b1 has a little different. So a1, c1 will be in the same bucket, and b1 is in another bucket. So whenever we have an overflow, then add a new page and increase the depth. So we don't have to increase the hash table, like we don't have to double the hash table, right? We don't touch these ones. Okay, in this case, we don't touch these buckets at all. And the hash function is doing the same thing. We don't have to rehash a0 and b0. we only have to rehash A1, C1, and B1. We have to handle the identifiers whose bucket has the overflow problem. Okay, so in this case, only 3 identifiers will be rehashed. Okay, good. So we can add new identifiers gradually without touching other identifiers. Okay, that is the beauty of dynamic hashing. Good. But still, we have a problem of try. Okay, that's not perfect. Okay, first, access time depends on the number of bits, right? Why is that? Look at this one. If we're interested in A1, then we have to go to this one and then check this one and then go to this one and then go. So we have to follow these branches a couple of times. Okay, so compared to the BST, binary search tree, what is the benefit? In the BST, then we have to compare the keys, but still, based on a couple of comparisons, then we can find our target node. So in the worst case, and the complexity is log n. Okay, so in this case, it is similar. So we have similar problems. So it's not actually hashing. The beauty of hashing is a constant time for access. So when we need an identifier, then the constant time is enough. That's the beauty of hashing. Of course, when we have overflow, then that's not a constant time depending on the situation, right? But as long as we don't have an overflow problem, okay, then just constant time should be guaranteed. But in this case, it's not just constant time. It depends on the number of digits. Okay, so we don't like that. Okay, so access time depends on the number of bits. That's not good. And second, if identifiers have a skewed distribution, tree is also skewed. That's another problem. Look at this one. If we have something like C1 and D1 and F1 and H1 and etc., then we will have overflow here again and again and again. So we have a skewed tree. Then we have same kind of problem as we discussed with the unbalanced binary search tree. So if the binary search tree is not balanced, then binary search tree is not working correctly, right? Worst case, we need linear time to find our target node. That's the worst case. That's why we talked about AVL tree to rebalance the tree, or a red-black tree. So rebalancing is necessary to guarantee log n time complexity, right? So in this case, if I have a skewed distribution, then the tree is also skewed, then that's not what we want. Okay, so try is not the best solutions. So we can actually change the problem. We can solve the problem with some tricks. So for the problem 2, we can use hash function. So in the problem 2, the identifiers have a skewed distribution. So if we design a hash function carefully, then this hash function can distribute all the identifiers evenly. Okay, then we can solve this problem. Good. So identifiers should be redistributed evenly based on the hash function. Okay, good. But what about the first one, access time? So to handle this problem, we can use a directory. Okay, so we'll talk about directory-based hash functions from the next slide. Okay, dynamic hashing using directories. Now we have 6 identifiers in the 4 buckets. Okay, so this one is actually the same as a try tree. Okay, look at this figure. So we have A0, B0, and A1, B1, C2, C3. So actually this tree is the result of the last one. Okay, but you know what I mean? So this one is actually also, it corresponds to a try tree. Okay, then now we insert C5. Okay, then C5 goes to this bucket. Then there is overflow problem. Okay, then what should we do? We double the directory. So I didn't explain how it works with the first figure, but let me explain how this directory works. So after doubling the directory, okay, now we have a 3 digits here. Okay, then A0, B0 is pointed by this directory and this directory. So look at these two. Actually, these two directories share the same kind of pattern, like 0, 0, right? So it means the first character doesn't care. Okay, so 0, 0, 0 or 1, 0, 0, they will point to the same bucket. So directory will point a bucket. Okay, one directory will point to one bucket, and multiple directories might point the same bucket. Okay, so now C5 had an overflow problem with this bucket. Okay, now C5 is here. Look at this one. So it corresponds to a try tree. So C5 is pointed by this directory with 101, and A1, B1 is pointed by this directory which has 001. Okay, so in this case they have the same kind of pattern, so 01, 01, but the first character is different. It's a 0 and it's 1. So A1, B1 bucket is pointed by only this directory, and the C5 bucket is pointed by only this directory. Okay, otherwise this bucket is pointed by this one, and the C2 bucket is pointed by this one and this one. It means as long as we have 1 0 at the end of this digit, then it goes to C2. And as long as the binary representation ends with 1 1, then it goes to this bucket. Okay, so the hash function will assign that identifier to a directory, and directory points one bucket. Okay, so now let's try one more time. So from this directory, now we insert C1. Okay, so C5 and the C1. So we insert C1. Now C1 goes to this bucket because it has the same kind of pattern, 0, 0, 1. Okay, now we have an overflow problem. Then what should we do? Whenever we have an overflow problem, then we double the directory. So this is our directory. Okay, then A1, C1 ends with 0, 0, 0, 1, and the B1 ends with 1, 0, 0, 1. Okay, so when the binary representation ends with 0, 0, 0, 1, then it is distributed to this directory, and that directory points this bucket. And if the representation ends with this one, 1, 0, 0, 1, then it goes to this directory which points this bucket. Okay, then let's look at A0, B0 bucket. A0, B0 bucket, we didn't actually touch A0, B0 buckets. Okay, so they don't have any problem so far. Then look at this one. This directory is pointing this bucket, and this directory is pointing this bucket, and A. So A means this one too. So this one is actually A. This directory is pointing this bucket, and we have another A here. Yeah. So this directory is pointing this bucket. So 4 directories are pointing this bucket. And what does that mean? This one has 0, 0 at the end of this representation. This one has a 0, 0. and this one has 0, 0, and this one has 0, 0. It means, the hash function might assign that identifier to this one, or this one, or this one, or this one, depending on the whole pattern. Then still it doesn't matter. As long as that representation ends with 0, 0, then it will point to this bucket. So it's like this one. So in the try tree, if it ends with 0, 0, then it goes to this bucket. Okay. But in this case, it goes to one specific directory, and then from that directory it goes to the bucket. Okay. So here's the thing. When we have an identifier, then we apply a hash functions to that identifier. Then the identifier goes into a directory first, and from that directory then we can go to a target bucket. Okay, so this one is indirect method. I mean, we have to go to the directory first, so we cannot go to the bucket directly. We have to go to a directory first, and then that directory will guide us to a specific bucket. Okay, that's dynamic hashing using directories. Again, in this strategy, whenever we need another bucket, whenever we have an overflow, then we need another bucket. So whenever we need another bucket, then we double the directory. Okay, so we might waste some memory space for directory, but compared to the bucket, directory is cheap. Okay, compared to the bucket, that's not that much. That's dynamic hashing using directories. And the directory size could be 2 to the power of k. So k is the number of digits. And it depends on the number of identifiers too. So in this case, we have 8 identifiers, and their binary representation is 6 bits long, but we need just 4 bits to distribute all these identifiers. Okay, so the depth 4 is enough. But for the worst case, if we insert like A1, B1, C1, D1, F1, H1, then it will increase the depth linearly. Okay, so then there is some chance to waste the memory space for the directories, even though that's not that significant compared to the buckets, but still. Okay, that's pretty much it. Okay, then for dynamic hashing using directories, then we have to handle a family of hash functions. So this family is required. So let's go back to this one more time. So when we have just 6 identifiers, then hash function should check only last 2 bits. Okay, so the hash function should read the last 2 bits. And then the hash function can assign this representation to a directory. Okay, but if the depth is 3, then the hash function should read the last 3 digits. Do you see the difference? In this case, the hash function should read the last 2 bits, but in this case, it should read last 3 bits. In this case, it should read last 4 bits. So whenever we increase the depth, then we have to have slightly different hash function. It's similar, but it's different, right? That's what this says. So hash function at the level I, it should read the last I bits. Okay. And if the keys are not uniform, then directory can grow quite large. Okay. If we insert like A1, B1, C1, D1, H1, then directory can grow linearly. So uniform hash function is important. If we insert A1, B1, C1, D1, then we have to come up with slightly different hash function. Instead of looking at the last bit, we might have to look at the first bit, from leftmost bit. Okay. So we should come up with better hash functions for some cases. Okay. then although it employs array doubling, it is faster than static hashing. That's what it said, right? So when we double the directory, then we might waste some memory space, but it's better than static hashing. And also, it is faster than static hashing because it rehashes, I mean the dynamic hashing using directories, okay? It rehashes only the entries in the bucket with overflow. So look at this one. We don't actually change this A0, B0 at all, okay? So we only focus on the bucket with overflow. And directory resides in main memory, and while the buckets are on disk. Yeah, it depends on the situations. If you have a large memory space, then you can have all the buckets in your main memory. But if you have the limited size of memory space, then maybe you might have a directory in the main memory, but buckets should be on the disk. But it depends on the situations. Okay. And there is another problem here. I already mentioned this issue. Okay, so the dynamic hashing using directories requires at least one level of indirections. As I said, in this case, hash function leads us to a directory, not to the bucket directly. From that directory, then we can go to a bucket. Okay, so let's say when we have one identifier, then hash function will lead us to one directory. Then from this directory, then we can go to a bucket. Okay, this is a constant, right? So compared to this try, in this case, we have to follow these edges. So a couple of steps could be necessary. But in this case, just one more step. Okay, that's enough. Just constant time, no matter how large it is. You know, when we double, then still the identifier can be distributed to one specific directory. Then from this directory, then we can go to some bucket. So two-step is fine. Two-step is that's all we need. Okay, that's constant, but still we wanna eliminate that kind of indirections to improve the speed. You know, the hashing is about the speed all the time. If we give up speed, then there is no reason to use the hashing. Okay, so you can use BST, or you can use just linked list, whatever. But when we use a hashing, it means the speed, the time matters. Time is critical issue. So even though it is just a constant time complexity, but we don't like it, then we want to eliminate that indirections. Okay. That's what directory list dynamic hashing. So in this hashing technique, we have a dynamic hashing, but without directory. Okay. So whenever an overflow occurs, okay, then we will add a single page at the end of file, so a single bucket at the end of file, and rehash the elements in the overflowed bucket. Okay, so that's basic idea. But when we have a linear dynamic hashing, and it might be a little different. So let's start from this try structure. Okay, we have 6 identifiers in 4 buckets, and we have a depth 2. Okay, then Q is pointing the first bucket, and then we insert C5. C5 has 101 at the end of the binary representation. So if we have just the 2 bits, then C5 is supposed to be in this bucket, and we have an overflow problem. Okay, good. So C5 makes the overflow problem, then we split this bucket. The Q is pointing this bucket. So we split this bucket, not this bucket. Okay, this is a little weird somehow. We don't split this bucket. Instead, we attach C5 at this bucket. So this bucket has overflow problem, but we have some extra space to store another identifier here. And instead, as I said, this one will be split. We'll split into two buckets. So the first one is here and the second one is here. So we add a new bucket at the end of the file. Okay, and then we have new identifiers for these ones, and this one, they have a 2-digit. Okay, so far so good. And then after splitting, then Q moves to the next one. So now Q is pointing this bucket. Okay, now Q is pointing here. Okay, and C5 is attached in this block, in this bucket. Now we insert another one, C1, ending with this pattern. So it is going to the same bucket, right? So now Q is pointing the second bucket, so we split this bucket. So we have another bucket, and this one is splitted. So A1, C1 goes here, and B5, C5 is in a new bucket. And now Q is pointing this one. Okay, so next we insert another one and another one. So whenever we have an overflow, then Q is moving to the next one. Okay, and then if we have another overflow, then we add another bucket at the end of this one, and Q goes back to this one. So now this one is our bucket file, and this one is the end. So now if we have another overflow, then we add another bucket at the end of this file, then Q goes from here to here, and then Q goes back. Okay, so this one is good, but there's no free lunch. It comes at a cost, right? So in this case, the hash function is complicated. What does that mean? So in this case, okay, let's look at this one. So in this case, we need the hash functions to assign this one and this one, this one, this one, this one. It means sometimes we have to look at 3 digits. Sometimes we have to look at just 2 digits. Okay, so fortunately, Q is actually pointing where this 2 digit starts. So this one we have to read the 3 digits, but from this one we need to read 2 digit, 2 digit, 2 digit. So this is the end of the file. So this one is just attached. Okay, so added, new added bucket. So we know this boundary. And then, when the Q is here, then we know where this 2 digit starts. So we have the hash function should read 3 digits, and it should read 2 digit and 2 digit. Okay, that's it. And the other ones, after this end of the file, the other ones we know we have to read the 3 digits. And then when we are done with this round, and then Q is again here, and then this is the end of file, then we have to read 3 digits. And when Q moves to the next one, then we have to read 4 digits for this one, 4 digits for this one, and this one we have to read the 3 digits, 3 digits, 3 digits. So Q is pointing where 3 digits starts. But anyway, this one is complicated. So hash function should know where Q is, and then hash function should read the proper number of digits to assign one identifier to a bucket. But anyway, without the directory, we can assign an identifier to a bucket, and then whenever we need, then we can increase the size of this bucket. Okay, and the difference between this approach and the directory-based dynamic hashing is that for 001 and 010, okay, if we have a directory, then we use a 001 and 101. Okay, So in this directory list dynamic hashing, so we don't have this one. In the directory based dynamic hashing, we can have this one as a directory. So this one is one directory, this one is another directory, and they can point to the same bucket. Okay, that's how it worked. But in the directory list dynamic hashing, so we cannot have this directory. So we can have only this one without this one. We can have only this one not as a directory, but as a just identifier. Okay, the sub-pattern of identifier. And hash function should be able to know how much we should read. So in the directory list dynamic hashing, hash function plays the role of the directory too. Okay, that's it. So this is the end of this chapter, and we talked about hashing. And hashing is about the speed. Okay, so when we look for one target identifier, then the hashing provides that service in a constant time. Okay, so that's the beauty of hashing. But sometimes we have to handle some situations like we have to design a nice hash function, and we have to handle overflow problem. And also if it is a static, then sometimes we have to increase the hash table. Or we can use dynamic hashing, so with the directory or without the directory. Okay, that's it.